So, hello everyone! I had this idea why I was watching this prime time live on Twitch. So he was writing Kruskal, I think it TypeScript or something. It was just a moment ago, and it inspired me to leave code alongside. So I was thinking, oh my God, how nice it would be if I just record while he's streaming how I am like live coding another solution, like a different solution. Just that came to my idea. It's really peasantry, like a very simple redneck like style, simple solution. So in the night here, it's really much in the night. Just saying, I was like, I was just like doing it. So that is fine, but you can ask like, why now this is not that live recording? And the solution is very simple. I will just show it. Because this was
union,
it.
right?
No. There is other ways to do this instead of unions. And I think it's just two arrays. And I will write it here again. Two arrays.
Yeah,
I will try to
I
write
think you can
it.
be friend group friends.
Leave.
I'm doing something wrong
So
here.
what we are doing
replace all the
is that 0 to 1
I heard that if put aside,
isn't a problem.
there's literally no. I'm regoing.
Maybe I
all
just
these
coded
dashboards
it
because I
badly.
haven't learned them.
Okay, let's see. If for loop. So I stop here, and you can see what the issue is. I recorded not the full screen, and you cannot see the whole glory of the code, neither the results in the bottom, neither anything. So I was really not happy about that, but here we are. Here we are. I will just go over the code. It's after I already finished it, like it was already finished in the live stream. And now when I was looking at the recording, I saw this like, oh my God, that is something's happening. Anyways, now I see that the resolution is well because you can see it somewhere. I don't know, I have seen it just a moment ago. Anyways, let's go around the algorithm a little bit. So what is this two-array algorithm? Okay, this peasant Kruskal two-array algorithm had this idea. First, let's define the edges. Like you see, there are like edges here. Very good. Then we will have an output array for the edges of the spanning, not tree, but spanning tree. Spanning tree or spanning forest. I didn't even dare to put it like a vector or something. I just like, it must be smaller than the input. And everything is inlined here. And you can see I just added 8 values, and I just encoded like from 2, and like that's how it is. It's very simple live coding in the night. I'm tired after work day and everything, so I didn't want it to overcomplicate it. Anyways, then we have some other things and some more things. First, this what group is the key here. The what group, basically, for every vertex in the graph, we are having this. That what group of vertices it's in. While building the thing. Where am I? I just move myself here to be somewhere in the corner. I don't know. It's fine. So, basically, for every vertex, we explain or store what group it belongs to. And what I mean by that, just remember this, what group, what means a group? First, we set every vertex as its own group, like they are separate. Because spanning tree, what it does, you need to access all vertices, except those that doesn't have any like edge to them or something. So we imagine that all vertices are separately sitting. Now, if we are getting an edge, of course, you are just sorting them like just in standard Kruskal. So this is the sorted list of edges, like 0, 1, 0, 2, 2, 3, 3 to 0. Just let's say. I didn't even wrote the sorting here because anyone can sort. Anyways. So, after the 0, 1, what happens is that we are unifying that the node at the 1, this is the, okay, so this is the column for the node number 1, and this is for node number 0. So basically first they are their own, but this can change, like what group they belong to. And if there is an edge from the 0 to 1, they will be in the same group, as you can see. It's like 0 and 0. And it's just how it is. If there is like one more edge from 0 that node 2, we can see that all of them are now sharing the same group. And if there is one more, all of them will be share the same thing. And now we will see that both sides of the edge share the same group, and we cannot add it because we would make a circle. And that's all. That's all we need. This what group array. So this is one of the arrays. One array. I talked about a two array solution. So what is the second array? The second array, or here I just made it a vector, but this is basically just a dynamic array. Like you make it once and it's there. It's like which group contains what. And the only thing that is not an array here, there are vectors inside. So for every group we have a vector. That's how it is. So this is basically inverse. This is the inverse operation. Okay? This tells what node belongs to what group currently. That's the invariant. And this, for this, the invariant is the opposite. Is the inverse function. Like the group, for any group, it tells what nodes it has. That's all. Okay, so basically you can imagine what is happening is that what is the reason for these other things, like not just this single array. So the second array needs to be there, because imagine that the order of the nodes in the second line here is not 0, 2, but like 2, 0. Then you cannot just copy over the value 0 to the number here, but because then you would copy over the 2 to the number 0, and guess what happens here? Here. That was on the same graph as the first, like the 0th element, the first and the 0th. So this should also become 2 in this case. You see what I'm talking about? And this becomes bad, and we are out of sync. So this is a mistake, and we can either order it, like this is like the easy tree. Like I show how often an optimization it is, but it does not need to be optimized. First, we just need to make sure that everything that was sharing the same value also becomes the value of 4. So how can you do that? Like there is a very brute force solution that you just see what is on the other side, and then you unify every value in the whole array, like in this line, to be like that. But there is a faster solution if you have the back references from the group contains, from the second array. So that is the one that I call the second array. Like we just use arrays, basically nothing fancy data structures. Of course, everything is just an array in the end, as it was told in the video, in the live session. Anyways, so that is how it is. This is basically what we are doing. J is the iterator on the output array, I is the iterator on the input array. You see we are going with every second step because that's how I represented the things. I was not like really caring for creating structs or classes or anything like fancy. And if the what group is like not different, then we can add that to the spanning tree. If they are different, then we are just not adding it and going to the next loop and trying something else, some other edge. Anyways, And what happens here is that we have the previous group and a new group. The previous group is what is the right side on the edge, what group it had, and what it will have. Will have is the left side of the edge. Just like this is simplification. And now we do some optimization here. What is this optimization? Is that we are saying if it is in the tree. That means that if we ever touch this vertex or not, if we never touch this vertex like ever, then we just set the what group, add it to the group contains, so the both arrays are updated, and that's it. Nothing fancy, it's like O1, constant time operation, and it happens for every edge. That's it. For this part. What is this other part? It means just the other direction. If, of course, it's an else if, so this was true, so the previous edge was in the tree, but now we are not, and this handles the opposite direction case. That's it. We just recalculate the new group and do these kind of things and do the opposite direction. And what happens if if basically both of them have been already touched? That means that we built subtrees like a forest, and we also saw that we can make a link between them, and there is an existing link. If there is no existing link, then this will be like subtrees, like a spanning subtree, like forest. But the thing is that if there is an edge, and we see that there is an edge because we are iterating on edges, and we can see and we can connect these two subtrees, and we need to join them. So basically what we're doing is that we just go around this group contains, and what we are doing, nothing fancy, we just override the new groups. So basically we unify them. And that's all. That's what we shown above in the comment. Except there is this little trickery here also. So this was an optimization here for the elements that were never touched. And we make one more optimization here, which is basically that if we merge on not symmetric two structures, like one is very huge and the other is like very little, tiny, small, then you know what these operations are doing here below is basically just like iterating over one of these, it doesn't count which, and make it look like exactly the other. But of course we should iterate over the smaller one and make it look like a bigger one's values, because that is like hugely smaller amount of work. And on average, like it's half the work. So on random data, basically, this makes like, of course, not a 2 times speed up, but like something very close. And that's it. That's the algorithm. Very simple, very peasant-y, very redneck style, very village style. Like I sit in a village and just wrote it like, why not? And of course there is print. And of course it just works. Basically what you see here is that we omitted the last two numbers because those would make like a circle in this case, and that's it. So it completely works. Very nice algorithm, very simple. There doesn't need to be anything fancy for doing this. And of course there is this to do here. If like your edges are not sorted by some kind of what is it, value, it's not called value, but like weight, that's the good term, then that's it. Sort by weight. You know how to call a sorting algorithm. The thing is that you can call actually some other exiting works is that you can call a Magyarsort here. That's like a linear time sorting algorithm, faster than ska sorting, and that's very fancy. And then if you don't do it this way, but you do it the other way of having binary trees for the groups and stuff like that many people do, then the algorithm can also go like nearly linear for this non-sorting other part. But the thing with that, I'm not sure if in practice doing binary trees and merging them, which is like something like O n log n log n, that O n multiplied by log many log n. So it's like very constant, very linear, like linear multiplied by constant in practice, but I'm not convinced it's faster for many inputs than this solution. Like this solution can be for a lot of inputs faster because it just operates on very small arrays, very basic operations. And what is the long part? Like these two very often happens and very fast. They are constant. Like basically that makes them linear to the edge number because for every edge they are called. What makes it slower is this part when we are iterating over the back reference arrays, and this makes them slower. But the thing is that what happens here? This is the slower part's even slow part because this is just preparation for an optimization. So this loop is the slow part, and what happens here is that we are just adding to a vector in a loop. That's very fast, that's very cache local, and we are just updating. That's also not so bad. So I don't know, there is not a lot of jumping in memory, there is some amount, but still might be better than doing some kind of tree data structures when it's a linked data structure generally. You can maybe trick that with some inlining in memory, but I don't know how to do that. So I don't know, this is just, unless you need to extremely optimize it for huge inputs, this is how I would do it. And if for huge inputs I would need to do it, I would roll out Magyarsort, which is like linear sorting algorithm. It's very fast, and then I actually that is already fast in like above like 60 elements. So I pretty much all the time use that kind of sort of mine. But you can use any kind of sorting like radix sort or something, which is only works when the data is big anyways, and then you could do the other solution with trees or something and very close to linear results. So for huge graphs you can do that. For small graphs or mid graphs I will just do this very simple solution or something similar. Maybe not exactly this, and you can of course code this with a little bit more clean code. And I'm not saying the clean code like a STM, like registered terminal bullshit, but like more readable or better parameterized, like then not just like inline magic numbers like here the 4 and the 8 and whatever, but you know what I'm talking about. So that's it, and this is the algorithm. Very short, very not fancy, and that's it. So yeah, actually many times just watching people on streams doing things can inspire you to come up with your own solutions. I don't know if this kind of solution to it is like written down or not. I'm pretty sure someone already came out with this already, because this is just so simple. Anyways, this is how I would solve it if someone asked me on interview or something. Anyways, video is still long. It would have been more fun if you see the live coding, but you see that there is proof of that, like here.
Union. Okay, so I did the exact same. You lost. What?
Also optimize the cape.
Oh, there was debugging too.
You get the idea. Like exchange, like.
And in the end, I was watching after there was some raiding of some other streamer. I just watched like what other people are doing. So goodbye, and have a nice night and day and whatever.